is to start with basically one of the two major types of energy that you always study in physics. So the first one is kinetic energy. Does anyone remember the definition of kinetic energy from the chart we did yesterday? It was the shortest, easiest definition. The energy of what? Of absolutely anything that is in motion. Okay? So the definition of kinetic energy is it's the energy due to motion. Energy due to motion, which means right there, if something has zero speed, how much kinetic energy does it have? Zero, right there. Could it, by the way, does it still have thermal energy? What did we say about thermal energy yesterday? It's the only energy that you can never make what? Zero. You can, why? Because for you to make thermal energy zero, what must happen to all the particles inside of the object? They must stop what? Moving and vibrating, which is completely impossible. So that means what? Thermal energy will never become zero. Anything else could, except thermal energy, which means motion could become zero if you have a completely at rest object. Okay? Any idea for the symbol? It's the same one we did in grade 11. It's an E, but we need a subscript. What do you think the subscript is? See? K. Yes, absolutely. So EK, uppercase, lowercase k, doesn't matter. What matters is the E has to be uppercase. Okay? All right. Oh, my bad. Sorry. Okay, so EK. Okay. This equation, as simple as it is one of the most fundamental equation in all of physics. In all of physics. So basically, the equation for kinetic energy is half times mass times speed squared. So what are the only two properties of an object that will actually make it have kinetic energy? Only what and what? Come on. What and what? What are the only two properties? Mass, it has to have mass. So the only particle that doesn't have kinetic energy in the universe is what? Light, is the photon. Because the photon has, by definition, zero mass. It's a pure fireball of energy. So mass. And it must be what? What's up? Oh, right here. Ah. So it's yeah. So I think I combined. Yes, I combined both. Everyone, I combined both slides. So the first box, everyone, the first box is for the word equation, and the second smaller box is for the math equation. Okay. So half mv squared. Let's check the units. I already did that for you. So half, is it a variable or just a number? Half. The half. It's a number, and numbers have no what? Have no units. Okay. So mass is measured in what? By default in standard units in kilograms. Great. Here's kilograms. Speed in standard units is measured in what? Just speed. Meters per second. But it's being what? In the equation, it's being squared. So it's kilogram times meters per second squared. Okay. Now let's play with the exponents here. Obviously, if you have a fraction subject to a power, what happens? It attacks here. It attacks here. All right. And here as well. Okay. So that's so far. Now, what am I going to do? I'm going to steal. I'm going to steal a power from the m's. So one power of the m's is going to be kept with this thing, and one power is going to what? Go here. So now here, what do you still measure using kilograms? Come on. Mass. What do you measure using meters per second squared? Acceleration. What do you get when you multiply mass by acceleration? Go back to Newton's laws. You get F net, right? And F net is a force. How do you measure force? Using what? Using Newton. So this whole thing is just a what? Times what? Times meters. What's a Newton times meter? Yeah, okay, hold on. This thing is mass times acceleration, right? Which is really just a force, and force is measured using Newton. What's Newton's times meter? Exactly, because Newton's measures what? Come on, Newton's measures force. Meters measures what? Distance or displacement. What's force times distance times cosine of theta, which has no units? That's a what? That's the equation for what? That's the equation for work, which is measured in joules. So technically, this equation is correct because unit-wise, it gives us joule at the end. Boom. That's it. Okay. Again, remember the first step they always do is check the units. If the units don't make sense, I don't care how much of a genius you are. Your equation has to be what? Manipulated to make sure that the units also make sense. Okay. So that is the equation for what do you call it? For kinetic energy of any object as long as it's going at certain speed and has a non-zero mass. Done. That's it. Either one of those parameters or variables is zero, the whole EK goes down to zero. Okay? All right. Now we go to what? Okay. Can I just see the notes? Okay. Don't worry about this one. I just want to run you through an example here. So, pencils down. This is not in your notes. Okay? All right. Suppose we have an object with a mass of what? 2 kilograms and the speed of how much? And the only reason I picked a mass of 2 and a speed of 3 is because then if you calculate the kinetic energy, it comes out to a simple what? No fractions, no decimals, nothing. That's all. I was worried about decimals because I have a what? I have a half, okay? But half cancels the 2, and then you get 9. So that means what? If an object has a speed of 3 meters per second at a certain moment and has a mass of 2 kilograms, it possesses, if it hits you, it gives you how much energy? It gives you a maximum, like there's no more kinetic energy in it, more than what? More than 9 joules. My question is it the same effect on the kinetic energy if you change the mass or you change the what? Or you change the speed? Well, let's see. Okay? All right. So the EK original is what? How much? 9 joules, provided it has a mass of 2 kilograms and has a speed of what? 3 meters per second. Okay. Check this out, everyone. What if I only change the what? What did I only change here? What did I only change? By the way, how many people know what a control experiment is? What do you mean when you say a control experiment? You only change how many things every time? One thing, because if you change 2 things, you don't know how much of your final output is due to what each change. So you only change one thing and you keep everything fixed. Okay? So the only thing I changed here is mass. My original mass was how much? 2. First, I what? I doubled it. So now what's the new equation? Half times 4 times still what? What's the speed still? 3. 3 squared though, right? 3 squared. So what's my new EK? 18. How about if you triple your mass? So half times 6 times 3 squared. What's your EK now? 27. What if you quadruple? Quadruple means multiply by what? 4. 4 times the mass. Yeah, 8 divided by 2 is 4 times. You get 36. Does that make sense? If you have a bigger mass and you hit something, do you give it more energy? Of course it does. So that makes sense. Okay, that makes sense. But apparently, can you see what happened here? When you doubled your what? When you doubled your what? What's the ratio between 18 and 9? 2. What's the ratio between 27 and 9? What's the ratio between 36 and 9? So what do you conclude? Whatever you do to the mass is the same thing that you do to the what? To the what? To the EK. That means if you double your mass, you have just the double of what? Of the original EK. Triple your mass, triple your EK. Quadruple your mass, quadruple your EK. Okay, that's fine. So it's the same effect. Check out what happens if you what? If you do the same effect, but to what? But the speed. If you double your speed, because your original speed was what? Your original speed was 3. So if you double your speed now is what? 6. So now it's half times the original mass, which was what? 2, but times what? Times 6 squared. How much do you get? How about if you triple your speed? How much do you get? 81. How about if you quadruple your speed? How much do you get? Is it the same effect of mass or much more? Why is that? You didn't even have to go to physics to explain it. Just look at the equation. What's the equation for EK again? Half mass V squared. What does that mean? Which one has a higher power? Mass or speed? Which means which one? So is the mass, so what do you call something with a power of 1? In math, what do you call something with a power of 1? Starts with L. Come on. Linear. So EK is linear in mass, but what do you call something with a power of 2? No. What? Watch out. Exponential is when you're what? Is when your x is on top, like 2 to the x, not x squared. What do you call x squared? Starts with a Q. Quadratic. So you always say EK is linear in mass, but quadratic in what? Quadratic in speed. If you double your speed, how much effect do you have on the EK? 4. If you triple, how much? If you quadruple, how much? Interesting. What's double squared? What's triple squared? What's quadruple squared? That's why it's always what? It's always better for you to manipulate your mass or your speed. Which one gives you, no, hold on. Which one gives you more kinetic energy for the same effect? Which one ended up having more kinetic energy effect? Mass doubling? Sorry, mass changing or speed changing? Speed changing. Okay, just so you know, everyone, this very simple idea is the reason why when they collide subatomic particles, they never collide big masses. They collide what? Small masses, because they're able to make them go very what? Exactly. You would rather have something small but go very what? Very what? Very fast than something bulky and big and go very what? Very slow. That's why if you ever watch any science documentary about collision of particles, you would never hear them say, "Oh, today we collided." Like for example, at the Large Hadron Collider, for example, when they smash particles together to basically smash them into quarks, you will never hear them say, "Oh, today we smashed two hydrocarbons or two sugar molecules." What's a sugar molecule? How many people know what a sugar molecule is? How big is a sugar molecule? Fructose and sucrose and glucose. How many people take biochemistry here or chemistry or biology? Those sugar molecules, are they small or long? They're very long chains of what? Carbon atoms with what coming out of them? Hydrogens, oxygen, nitrogens, depend. Is that a small mass or a big mass in the particle world? That's a big mass, which means what? Is it easy to speed up or hard to speed up? Remember inertia. What's inertia? Which one is easier to what? To push in space? A tennis ball or a fridge? Which one is easier? A tennis ball, because it has a small what? Has a small mass, has a small inertia. It doesn't fight as much. So that's why they always collide what? Big particles or big molecules or small molecules. Why? Because when you have a small molecule, you can actually do what to the speed? Speed it up, which means you can actually get a very high value of what? EK. And then when they smash, they actually destroy each other or basically break the two spheres into the quarks inside of them. Do you see what I mean? It's better for you. It's more bang for your buck, as they say. It's more investment return if you change your what than to change your what? Yeah. Okay. All right. So changing speed affects kinetic energy more than changing mass. And that's all I wanted to do with this slide. All right. Do we have this problem? Or maybe a different one? Yes. Okay. Calculate the mass of a blue jay, a bird, blue jays, moving at 15 kilometers per hour and having right at that. What's up? Oh, don't worry. We're coming back to that. I just put the two slides together. With 0.83 joules of kinetic energy at the moment when it has a speed of 15 kilometers per hour. Okay. What's the first problem in this problem? What's the first inconvenient issue? Can't be, right? Because everything, by the way, joules, it's a what unit? It's a standard unit, which means it comes only from what? Standard kinematic units as well, which means that has to what? Change to meters per second. Who remembers the quick trick? I mean, you are more than welcome to do the convergent unit sheet we did at the beginning of the course. But what's the quick trick to jump between kilometers per hour and meters per second? What's the magic number? 3.6. Now comes the question. Are you going to times it by 3.6 or divide it by 3.6? I have a very easy way to get you to remember. How many people say times? How many people say divide? It's divide. I'll tell you why. Hold on. I'll say one thing. You will never forget it. What's the time unit here? Hours. Do I want to expand it or shrink it? When you shrink, what do? That's it. Always remember it that way. You have an hour. You just want to take it to one what? 1 second. So are you going to expand it or shrink it? Shrink it. So you divide by 3.6. That's it. Always remember. You are going from a big time scale to a small time scale. So, oops, sorry, my bad. All right. So first of all, 15 kilometers per hour divide by 3.6. Who's got this? Is it an infinite? Yeah. So 4.27. Yeah. 3 sig figs because we have two. Oh, 1.7. Okay. Okay, now what do? I just plug in the easy equation. So EK, everyone, EK equals half mv squared. Which two symbols do I know here? Which two variables do I know? Yes, Ayat? I know the EK, and what do I know on the right side? I know the speed. Somehow I need to find the V. Sorry, the mass, I mean. Okay. Um, you know what? I know it's easy enough to do with numbers, but let's do it with symbols today. All right. How would you, everyone, if you did not have numbers and you're trying to solve for M, what would be your first algebraic step here? Raise your hand if you have an algebraic step. There's a couple of ways, but what would you do first? Anyone? Ahmed, Wadah, what would you do? Times it by 2. Why? Because then you get rid of the fraction and you move the 2 to the other side. So if we times it by 2, it becomes 2ek equals mv squared. Okay, almost there. What's my next step? I'm solving for mass. So I need to divide both sides by the square of v squared. So m equals, no need for a square root because m is already linear. So 2ek divided by v squared. Done. That's it. So it is 2 times 0.83 divided by 417 to the power of 2. Who's got this? Obviously, it's supposed to be a small mass. I mean, look at the question. It's a small bird. So what's the mass? By the way, whatever you get the mass in, standard, it's got to be in what? You started with standard. You have to end with standard. So what do you end up with? You end up with kilos, exactly. So kilogram. And you have to give me the answer to 2 sig figs because 15 and 0.83 are both up to 2 sig figs. What do we have? Apparently, is the answer 0.095? Great, 0.095 kilos. Now, in university, sometimes you might get a half mark deducted because you would leave it like that. Why? I mean, physically it's correct, but what's a bit inconvenient about that number? It's very small in the kilogram scale. So what's a good scale for this one? Grams. How many grams in a kilogram? Whenever you say how many things in a kilo of those things, it's 1,000 meters, 1,000 kilometers. Sorry, a kilometer is 1,000 meters, and so on. So if we multiply that by 1,000, I don't need to do any work. I'm just going to half this 3 times. 1, 2, 3. So it is 95 grams. Done. That's it. Which makes sense. You wouldn't expect it to be any heavier. Okay. All right. Makes sense? Okay. Next question. Oh, okay. Actually, hold on. Okay. So let's read this question. An archer pulls back her bowstring loaded with how much of a mass? 22 grams or 0.022 kilograms arrow, and then releases the string. The arrow speed as it leaves the bowstring is how much? 220 kilometers per hour, double highway speed. That means there's a lot of elastic energy stored in the string, which was completely transferred to the arrow to push it forward. Question is, calculate the work done on the arrow by the bowstring. Okay, can someone tell me what's the equation for work that I taught you a week ago? I taught you so far an equation for what is it? W equals what? F times distance times cosine theta. Do you have any force information in this problem? Are you told how much force is acting on the arrow? Are you told how much distance it moves? Is that equation useless or useful for us? It's useless. I have no force information. I have no distance. Is there another equation for work? Yeah? Taught yesterday. Come on. Ahmed? Say again? Change in energy. Change in energy. Is this arrow gonna move? Which means if something is in motion, what energy does it have? EK. Do you have the mass of the arrow? Nice. Do you have the speed of the arrow? Perfect. You see? You will always, in university, you'll always have a formula sheet full of equations. Some equations, and they solve for the same thing. Some of them are useless because you don't have the given variables, and some of them are the ones you need to know. You just have to decide which one is useful. All right. So it started here. Everyone look. And it ends there. Such that once it leaves, what speed does it build up to? Build up or accelerate to? 220 kilometers per hour. Okay, so everyone, let's do this. So initially, everyone, initially, is the arrow moving? So what's the EK of it right now? You're holding it. 0. Do you even need to show me a calculation for that? Nope. You can just argue it by saying no motion equals 0 EK. Great. All right. How much speed do we have here? It just left, which means no contact with the string anymore. 220. But 220 what? Kilometers per hour. We need to do the trick again. What do we do? Divide by 3.6. Everyone go ahead. 61.111111 forever. I chose 2 digits after the decimal point. Okay? Go ahead. Come on. Okay. So this is the way I'm going to approach it. No force information, no distance information means this equation is useless. Doesn't help me. I have no idea how to plug things in it. Okay, so we go to the other one. All right. Without showing any work, what's this number? Because it's the initial state of the arrow, which has no motion. What's the equation for E final? By the way, technically, should you also add another subscript to each one? What kind of energy are we only concerned with now so far? EK. So everyone, let's actually write EKF, because we're going to have, by the way, we're going to have a lot of energies in this course, and we're going to have systems just like you had systems with, just like you had FBDs with multiple forces. You're going to have systems with multiple energies in them. So labeling is important. So everyone, just write EKF, EKI. Okay, what's the equation for EK? Whether it's final or initial. Only one equation. What is it? The equation for EK, half mv squared. The only difference is, what's my v here? It's v what? And v here is v. Great. By the way, does the mass change? No, mass never changes in any physics problem unless you're told it does. An object stays the same mass the whole time. All right? How many people agree with this equation? What kind of common factors could I take out from both terms? I can take the mass because it's the same number each way, each time. How about what's another common factor as well? Half. Okay, you can do that. But there's an easier way. What's the entire second term? Great, cross it out. Why bother with common factors when 1/2 of the equation is completely eliminated? Great. All I have to do now is multiply half by the mass of the arrow by the speed squared. Speed in meters per second, of course. Done. That's it. What does this mean? The arrow has imparted. What does impart mean? What's another synonym for impart? Import you take, impart you give. The bow gave 41 joules of energy that was stored in it. It's not stored anymore because it's been converted to what energy? Remember, the only energy that's never potential is what? Kinetic. All energies, all other energies are potential because they potentially could be stored, except for energy, except for kinetic. Because when you move, you're not storing. You're actually using up your energy. You're burning it up. Okay, so 41 joules. That's it. Okay, so that's a good example explaining to you how you still can calculate work, even though you don't know force, even though you don't know theta, even though you don't have an FPD, even though you don't have a distance information. Okay? All right. That's all we need to know for today about EK. What's the other kind of energy that we have to study today as well? Kinetic. What's its twin? Twin is gravitational. Yes. All right, so let's go to the next slide, or to a former slide in your notes. Okay. Question for you, everyone. Listen up. Hold on. Yes. How many objects do I have in my hand? Eyes on me. 2. Okay. Am I holding both of them at the same? By the way, I don't like to say the word height. I like to use the word elevation. Why do you think I don't like the word height? Because to me, an object's height is what? My height. You see what I mean? Like an object's height is related to its size. But elevation means what? What does elevation mean? Exactly, the distance to the ground. So I'm always going to use the word elevation. The book might use height. So, because again, do we really care about the size of an object in physics? No, because everything is a dot. But I will still use the word elevation. Am I holding these both at the same elevation? Okay. Do they have the same mass, though? Okay. So if I drop them, which one would, if I do, which one would dent the floor more? Eraser or this? So do you think that mass factors in how much energy is imparted into the floor? Great. So mass must appear in the equation. All right. Now I'm going to have two identical objects of the same mass, but now different elevations. Thank you. Different elevation. And I'm going to drop them. If there's a paper underneath each of them, which one might rip through the paper? This one or this one? Why? Because by the time it reaches the paper, it would have built up to more what? More. It would have okay. It would have built up to more speed because it would have experienced a longer time to accelerate. You see? By the way, does it build up to more acceleration, or is it the same acceleration both of them? Yeah, it's 9.8 for both. It's just this one has a higher distance to what to travel through and to build up speed. So that means what? Does elevation matter? Yes, it does. Okay, last one. If I hold this here at a distance of, let's say, like a bit more than my height, which is like 2 meters, and I drop it, and I take it to the moon, and I do the same thing, which one would cause more dent? On Earth? Here. So what also factors in? Gravity. Exactly. How much the gravitational acceleration of the planet is. Can you think of any other factor? We talked about mass. We talked about elevation. We talked about the type of the planet, or sorry, the gravitational. Okay, air drag. Do we ever care about that? Nope. We care about friction unless it's in a medium. We always say air drag is completely negligible. Otherwise, the question is so hard to solve. Again? No, I just want to hear. Initial speed, true. But we're always going to what? We're always going to be holding it first and then dropping, which means always the initial speed is what? We're controlling that part of the experiment. But that's a good observation. Can you think of anything? Do we ever care about the material of it or something, or the elasticity of the object? It does factor in, but do we care about it in physics or in engineering then? Engineering. We're doing the physics. That's it. The only three things you have to worry about in gravitational energy are what? What was the first thing? Mass, elevation, distance, elevation, and gravity. Perfect. So gravitational energy, gravitational potential energy is the energy due to the elevation above the surface. Surface of what? Surface of a planet. Surface of a planet. When you're on the surface, what's your gravitational energy? 0, because if you release, nothing happens. You need to be above for you to see some motion once you release. Okay? All right. Any idea for the symbol? Small g or capital G? Small. For one reason. You have to be very what to the surface to experience EG? Close. There you go. And whenever you're close to the surface, is it the gravitation or gravity when you're close to the surface? Is it gravitation or gravity? Gravity, which is the small g. Yes. Very good. Okay. Is this, sorry, a more complicated or an easier equation now? Can you tell me if anything is squared in this equation? What does that tell you about the changes? If you double your mass, what happens to your EG? If you double your elevation, what happens to your EG? If you double your G, like if you go to a planet with double the gravitational acceleration, what also happens to your EG? There you go. So this equation is what? Is different than the other one because that equation was not the same with mass and v. This one is the same with all because all of these variables have what power? 1, not 0. 1. If a power does not appear, you're in functions now, you should know this. If a power does not appear on top of a what? On top of a variable, it's a what? It's a 1, not a 0. Why is it not 0? Because of this rule we used in teaching grade 11. Anything to 0 is what? Anything to 1 is the box itself. That's why it has to be 1, for it not to change. Let's check the units. Kilogram for mass. G is an acceleration, which is this. And elevation or height or distance is mass. Guess what? It's the same thing. And it's already split up for us. Mass times acceleration is newtons. Newtons times mass is joules. Done. This equation checks out. Okay. Let's go to the next slide where we compare the effect of m and h when you change them, just like we did for the speed and mass. And he pushed me off a building. Again, as long as you're on top of the building, you have potential. Once you're pushed, you're converting it into what? Into motion. You have less and less potential as we say goodbye to you. Okay, same thing. Now I'm using 5 and 3. Why? Because there's a decimal here and I don't want it to affect my final answer. So 5 times 9.8 times 3, 147 joules. Okay, what are we going to change first? By the way, so question for you. How easy is it to change the mass of an object? Easy. How easy is it to change the elevation of an object? Yeah, I just lifted my hand up. How easy is it to change G? You can't. What do you have to do to change G? Literally, you have to go to a different planet. So you always talk about just M and H in the equation. All right? If you double your mass from 5 to 10, what's the ratio between 294 and 147? It has to be the same effect because it's linear. You triple, you triple. You quadruple, you quadruple. Okay, how about if you change your what now? Your elevation, but you keep your mass the same. Are they the same numbers? There you go, which means what? As far as math is concerned, either changing the mass or changing the elevation in the same way does not make a difference. It made a difference for speed, but it does not make a difference for EG. There we go. Changing mass affects gravitational energy as much as changing elevation. No more, no less. Exactly the same. Okay. And here's the, oh, yes, everyone, just so you know. Do you have that warning in your note? Yes, you do. Okay, everyone. This is super important. You don't have to write anything, just listen to me. Whenever you're doing a problem where what? Where what? Gravitational energy is concerned, you need to be very careful about what you designate or what you choose as your what? Your reference height. Everyone, listen up. Your reference height can be anything you want. But two things. Number one, whatever you choose, you stick with it until the end of the problem. You do not say, for example, let's say, by the way, usually, what do you think reference height is? Usually, what do you think the reference height is? The ground. Yeah, 0. Sorry, what do you set as 0? The ground. Can you set 0 to be the height of this desk? Can you set it to be the ceiling? You can set it to be anything you want. Two things, though. Number one, whatever reference height you choose, you consistently use it throughout the whole problem. Okay, that seems fair. The other thing is where people might what people might forget, and then it screws up the problem. Anything above the reference height is given what kind of what kind of y value, positive or negative, just like math. And anything below it is given what? Is given. By the way, is there anything negative about my hand right now? Nothing physically, but mathematically speaking, is there anything negative about it? Yes, because we need references in math, which means we need them in physics as well. Any object below the chosen reference height must be given a negative elevation. If you don't, and you give it positive, that will end up meaning it's what? Meaning it's what? Above the reference height, which it isn't. So always remember, if something is below, it has to be what? It has to be a negative value for elevation. So personally, I almost choose the ground as the reference level. Although you're going to see that some problems, you are better off choosing what? Choosing what as a reference height? Something other than the what? Yes. In fact, choosing the ground is going to overcomplicate the problem. It's still solvable, but it's just gonna take a much longer time. No, change your reference height if you see it's more natural to the problem. Most of the time, ground is good. Sometimes it's not. And when we do a lot of EG problems next week, you'll see what I mean. Okay. All right. Here's a quick problem. Okay. A gray squirrel. I love the fact that they had to specify the color, because if it was a different color squirrel, physics doesn't work. Gray squirrel drops. Drops. What does drop mean? What's the initial speed? 0. Your release. Drops a 0.02 kilogram or a 20-gram walnut from a branch that is 8 meters high. High above what? By default, if they don't give you something, you know it's high above the ground. Determine the change in potential energy. You see, that's why I don't like textbook. You see what they called it? They called it what? Potential energy. But we said all energies are what? Except for kinetic. What potential energy are we talking about now? Say, that's why I'm never going to say potential. I'm just going to say gravitational energy. I'm going to be very explicit about which one in the chart we're dealing with. Of the walnut between the initial branch height and the ground height, which is 0. Okay. Question. Determine the what? What's the symbol for change? Delta. So they want delta. Everyone, they want delta EG. Okay, what's delta EG? If you want to expand delta, what do you say? Any delta is always what? Final minus. So EGF minus EGI. Okay. Okay, so everyone, let's just sketch a quick diagram. Not moving. Moving. Okay. What's the equation for EG? What's the equation for EG? Whether it's final or initial. M times G times H. So M does not have a subscript because the same mass, same G, but elevation is final. Minus M, G, elevation is initial. All right. Which one of those is 0? Which one is 0? Initial height or final height? No. Which one is 0? Initial height or final height? Final. Again, we're taking the 0 to be the ground, which means above it is basically what? 8 meters. This is 8 meters. So which one of those two would be completely 0 by the time it reaches the ground? Final. So right there, this is 0 just because of this one. Sorry. Which means what's your final answer? Just minus M, G, H, I. And now we're ready to what? Plug in the numbers. Minus, the mass is 0.02 times 9.8 times 8.0. Okay. Sorry. Who's got this? In Joule. Because I want to comment about a couple of things in these correspondence that many of you probably are thinking about right now. Who's got this number? I know it's a negative. I just need the number. Anyone? The question says, the answer says 1.6. Is it? 1.56, but since we have 2 sig figs and 2 sig figs, it is 1.6. Done. Here's my question. How come the answer in the book used the positive? or sorry, left it as a positive, I should say. They didn't use it, left it as a positive, or expressed it as a positive. They kind of described it to tell you that it was going down. What'd you say? I just didn't hear. Mm-hmm. Anyone? Why do you think they gave you a positive answer instead of, like, why did they ditch the negative? I don't agree with what they did, by the way. Okay, you're already knowing it's losing energy, but we know it because of the negative, right? Yet they did not put it in the final answer. Wadah, what's your argument here? No, okay, because question for you, everyone. As it goes down, does it have more EG or less EG? What more does it build up to? EK. Do you see the conservation of energy in play? Whenever you lose one, you what? You get, which makes sense. That's why when you drop something, does it slow down or speed up? Because one EG is seeping into what? Into EK. Remember the bars we did in grade 11? We're going to do them tomorrow when we do energy conservation. But my point is still, why did they not use the minus in the final answer? Or, here's another question. How could you change the question to justify not using the minus? Aha. Okay, I'll give you a hint. If I ask you right now, how much did you lose in the stock market? What do you just tell me? Do you tell me minus $100? What do you just say? $100. Why do you not say the negative in that particular question? Because I said what? I said how much. What are two other words that could stand in for how much? Amount or magnitude. See, if the question says determine the magnitude of the change, then we don't need a what? Sorry, not only we don't need, we should never use a what? When you hear magnitude, amount, or how much, you are not to use a negative, right? Even if it's in the final answer, because the question already just asked for what? The amount of change. Is there any word here that stands for amount? No, they just said what? Determine the what? They changed. They did not say amount of change, how much change, or magnitude of change, which means what? Can you ditch the minus? They ditched it because basically they just wanted the what the. But again, is it clear in the question? Not in my book. No, I don't agree with that. So if I give you a question like that, do I expect the minus to still be there? Yes, I do. Done. That's it. Okay? Perfect. I want to. Oh, the other thing I want to comment about. Everyone listen up. I always have people asking, how come there's no minus here? Okay, raise your hand if you actually thought about that. Okay? Why do you think there's no minus there? I mean, you could argue it's going down. I'm not saying it's not. When do we only use minus with the 9.8? Only when we did which unit? Kinematics, yes, because things could be what? Speeding up or you could be designating something to be going positive up or going positive down, right? Here, I just care that what? That the 9.8 is how much the what? How much the gravity of the Earth is pulling it down. Where's the minus going to come from? From the delta. Is it making sense now? Never put negative 9.8 in energy. Just use it as the actual strength of the planet itself.